Welcome to chemistry classes. In this video we are going to discuss about grade 11 chemistry. Grade 11 chemistry, classification of elements and periodicity in properties, part 3. Okay, so here first we have to discuss here classification of elements based on their properties. Elements in periodic table we can classify metals, non-metals and metalloid. Okay, mainly elements are classified based on their properties. Based on their properties, elements are classified metals, non-metals and metalloid. Okay, and we know there are many examples for metal: silver, gold, platinum, sodium, potassium. Okay, S block elements, D block elements and F block elements are metals, and some of the elements in P block also metals. Around 78% of elements in periodic table are metals. 78% of elements are metals. Okay, we know metals are good conductor of electricity. Metals are malleable and ductile. Metals are sonorous. They are good conductor of electricity and heat. Okay, these are the major properties of metals. Non-metals. Okay, few percentage of elements in periodic table are non-metals. Okay, here example for non-metals: nitrogen, oxygen, helium, neon, argon, hydrogen. These are non-metals. Most of the non-metals are poor conductor of electricity except carbon. Carbon in the form of graphite is good conductor of electricity. Carbon is one of the element in non-metal. Carbon exists in different form: graphite and diamond. Okay, so graphite and diamond are different form of carbon. Okay, graphite is good conductor of electricity, diamond insulator. Clear? Also here we have to understand here most of the metals are okay. So here we discuss about metals. Next one, non-metals. Non-metals also we discussed properties of non-metals. Non-metal exist solid state, liquid state, gaseous state. Okay, most of the metals are solid state except gallium and cesium. Other elements are solid state at room temperature. Okay, but most of the non-metal exist in solid state, liquid state, also gaseous state. Clear? Also here we have to understand, I told you melting and boiling point of non-metals are comparatively less, and non-metals are poor conductor of electricity except carbon. Carbon in the form of graphite, it is good conductor of electricity. Okay. And here when you check the periodic table, in periodic table when you are moving from left to right across the periodic table, metallic character decreases. The left part of periodic table metal, right part of periodic table it is non-metal. Okay, so metallic character generally you can say metallic character increase. Finally it will be non-metal. For example, S block elements, compared to S block elements and D block elements, metallic character increasing from S to D block. Okay, but right part of the periodic table all are non-metal. Okay, group 18, group 17, these are non-metals. Clear? You can check here periodic table between metals and non-metals there is a zigzag line. This zigzag line separate, or these elements separate metals and non-metals. These elements are called, the elements which coming in zigzag path, These elements are called metalloid. Okay, here example for metalloid: silicon, germanium, arsenic, antimony, tellurium. These are example for metalloid. Metalloid shows both metallic and non-metallic character. Clear? So these are example for metalloid. Metalloid shows both metalloids, they shows both metallic and non-metallic character. Okay, next one we have to discuss here periodic trend in physical properties of elements. Periodic trend in physical properties. Physical properties, first we have to discuss here atomic radius. Okay, so here we have to discuss here periodic trend in physical properties. First one, atomic radius. Radius of atom. We know atoms are microscopic and it is very hard to measure radius of an atom. Also, there is no fixed boundary for an atom. Without a fixed boundary, we cannot measure radius easily. Okay, so here you have to understand atoms are microscopic. Okay, also there is no fixed boundary for an atom, so it is very hard to measure radius of an atom. Clear? Also, we know atoms are microscopic, so radius of an atom radius of an atom measure in picrometer, pm. Clear? Also here radius of an atom cannot measure in free state. One atom in free state we will not measure its radius. Generally we will measure radius of an atom in combined form. Okay, for example, we want to measure radius of chlorine. Okay, so we have to look not in chlorine, we have to take chlorine, 2 chlorine atom in combined form. Okay, then we will measure distance between these 2 chlorine atoms. Okay, using this distance we can measure radius of atom. Okay, so radius of an atom not measured in free state, but we will measure in combined state. Okay, combined state. So here we know there are different type of elements, metals and non-metals. So measurement of radius in metals and non-metals are different. Okay, so first one we have to discuss here radius of non-metals, radius of elements, such type of elements like non-metals. Okay, so radius of non-metals generally we will call covalent radius. We know covalent bond formed between non-metals only. Okay, so we want to measure radius of one non-metal. So generally we will not measure in free state, we will measure radius of this type of elements in combined state. Example, I told you chlorine, we want to measure radius of chlorine, so we will not consider one chlorine atom. We will take 2 non-metals, they are combined by covalent bond, single covalent bond. We know multiple covalent bond, single bond, double bond, triple bond. So 2 atoms are joined by a single covalent bond. Distance between these 2 atoms, it represents covalent radius. Okay, covalent radius. Example here Cl2. 2 chlorine atom joined by a single covalent bond. Okay, and this bond length is 198 picometer. Okay, 2 chlorine atom joined by a single covalent bond and this bond length 198 picometer. Using this we can measure radius of one chlorine atom. Half of this 198, it's half, 99 picometer. So this is the radius of chlorine atom. Clear? Okay, so here we discuss covalent radius. Covalent radius, it is related to non-metals. Next one we have to discuss here metallic radius. Radius of metals we will refer metallic radius. Okay, metallic radius we can say half of the distance between two adjacent nuclei of two adjacent atom. Okay, you can see here crystal. Okay, a metal crystal, it consists of many metal atom or many metal ions. Okay, so half of the distance between two adjacent nuclei. Okay, half of the distance between two adjacent nuclei of metals, okay, in a crystal system. This distance called metallic radius. For example, copper. When you take copper metal, a piece of copper metal, distance between two adjacent nuclei of two adjacent copper atom, this distance is 256 picrometer. So half of this distance, that is metallic radius of copper. Okay. So distance between two adjacent nuclei of copper atom, that is 256 picrometer. Half of this to 128 picrometer. So this is the metallic radius of copper. Clear? So here generally you can define metallic radius. Metallic radius mean half of the distance between the nuclei of two atoms, or you can say two metal ion in a crystal system. Okay, so sometimes in a piece of metal, this metals can lose outer shell electron very easily, then it form a sea of electron and it will be metal ion. So you can say here two adjacent metal atom or two adjacent metal ion. Okay, so when you take two adjacent metal ion or atom, distance between these two nucleus, take this distance and take its half. This half distance, that is metallic radius. Clear? So we discuss here copper 128, metallic radius of copper, it is 128 picrometer. So here we are talking here radius of atom. So radius of atom we can say different way: metallic radius, covalent radius, van der Waals radius. So what do you mean by van der Waals radius? This van der Waals radius and covalent radius both coming in non-metals. Both are related to non-metals. Clear? So here covalent radius mean two adjacent atom, they are bonded by covalent bond, single covalent bond. Half of this bond length, that is covalent radius. But sometime helium, neon, this type of elements are monoatomic elements, single atomic elements. They do not make covalent bond, single covalent bond. Okay, but when you take some sample of helium sample, two adjacent atoms will attract by weak van der Waals force of attraction. Okay, two adjacent atoms are attracted by weak van der Waals force of attraction. This force of attraction, not covalent bond, weak van der Waals force of attraction. Now distance between nucleus of these two adjacent atom, this distance is called covalent radius. Clear? So here we discuss radius of an atom. We can say metallic radius for metal, covalent radius for non-metal. They make single covalent bond. Van der Waals force of attraction, also we can use this type of elements: helium, neon, argon, krypton. Okay, single atomic elements. Okay, so we will use here van der Waals radius. Okay, next one we have to discuss here trend in atomic radius. Okay, So here trend in atomic radius mean here we have to understand when we move across the period what happened to atomic radius. When we move down the group what happened to atomic radius. First we will see when we move from left to right across the period atomic radius generally decreases. Generally atomic radius decreases across the period. See here one example. This is one period: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Okay, so you can see here atomic number increases across the period. Atomic number increases. Atomic number 3, 4, 5, 6. It increases till 10. Okay, so here you can see here number of orbit. Here number of orbit, all case number of orbit will be 2. Okay, 2 1, 2 2, 2 3. Electronic configuration will be like this. First shell 2 electron, second shell 1 electron, 2 1. Here 2 2, 2 3, 2 4, 2 5, 2 6, 2 7, 2 8. So all case there are 2 orbit. Okay, so here number of orbit not increasing. Okay, number of orbit constant, or you can say shielding effect. You know shielding effect. Shielding effect also stay constant. Clear? So but you can see when you move across the period effective nuclear charge increases. Effective nuclear charge mean positive charge of nucleus increases from left to right. Okay, because number of protons increases. But inner shell inside this there are only one orbit. Okay, all case there is 2 orbit. This is outer shell and this is nucleus. Inner shell mean shells between nucleus and outer shell. That is inner shell. This inner shell electrons they make a barrier between nucleus and outer shell electron. This barrier called shielding effect. If there are many orbit, there will be more shielding. But all case there is only one inner shell. So you can say shielding constant, shielding not increasing. Okay, inner shell not increasing, it is constant. But you can see number of protons are increasing. Here 3, 4, 5, 6, 7 till 10 number of protons increases. So nucleus attract outer shell electron more effectively. So size of atom decreases, atomic radius decreases. Okay, so across the period atomic radius decreases. Similarly, when you move from top to down, when you move from top to down, atomic radius increases. Okay, when you move top to down, for example, you have lithium, sodium, potassium, rubidium, cesium, francium. When you move like this, what happened here? Here size of atom increases. Size of atom increases. Number of orbit, atomic number increasing. Here 3, 11, 19. So here atomic number increasing, number of inner shell orbit increases. So size of orbit increases. So you can say down the group atomic radius increases, across the period atomic radius decreases. Look here. Here we discuss across the period atomic radius decreases, but there is one exception case. Okay, group 18 elements. We know group 18 elements, they are monoatomic, single atomic element. They do not make covalent bond, they are single atomic element. Okay, so there is exception case for group 18 compared to other elements. Group 18 element shows higher atomic radius, because they are single atomic elements. Okay, they do not make single covalent bond, and their atomic radius is bigger compared to other. So here we discussed atomic radius generally increasing. Okay, so here noble gases, helium, neon, krypton, xenon, okay, so they have exception case. They do not make single covalent bond, they are monoatomic, so their atomic radius is bigger compared to others. Clear? So these are the things. So here we discuss across the period atomic radius increases, generally atomic radius decreases across the period. Also we discuss their reason for that. Also we discuss down the group atomic radius increases, we discuss their reason. Clear? Okay, so here next property we have to discuss here, ionic radius. We already discussed atomic radius. After atomic radius, next one we have to discuss here, ionic radius. Okay, to discuss ionic radius we have to know two points here, cations and anions. Cations mean atoms with positive charge. Atoms with positive charge. For example, Na plus, Mg2 plus. These are cations. Generally, metals are cations. Okay, atoms with positive charge, they are cations. And anions mean atoms with negative charge. N3 minus, F minus, O2 minus. These are anions. They have negative charge. Clear? So cations and anions. So here distance between cation and anion in a crystal lattice or crystalline compound. Okay, this distance, it is called ionic radius. Ionic radius means radius of ion, radius of cations or radius of anion. Okay, so that is ionic radius. So simply we can say distance between a cation and anion in a crystalline compound. This distance, it is called ionic radius. Clear? So radius of cation comparatively compared to its parent atom, radius of cation will be small. Cation means less number of electron. Atoms with positive charge, that is cation. Cations have less number of electron. Anions mean Cl minus. Anions mean negatively charged atom, and they have more number of electron compared to parent atom. Anions, they have more number of electron. So cation, number of electrons less. So size of this atom is less than parent atom. Okay, size of cation is smaller compared to parent atom. Clear? Similarly, size of anion is bigger compared to parent atom. Size of anion is bigger compared to parent atom. Clear? So here size of anion is bigger. Cl minus, radius of Cl minus is bigger than Cl, because there is one extra electron. Also, if there is one extra electron, there will be electron repulsion, inter-electronic repulsion. Because of this inter-electronic repulsion, here radius of anion will be bigger. Clear? So here we discuss ionic radius, cations, anions, distance between cation and anion in a crystalline solid or crystalline substance, that is ionic radius. Radius of cation is smaller compared to parent atom. Radius of anion is bigger compared to parent atom. After that, here we have to discuss here isoelectronic species. Isoelectronic species mean different ions, they have same number of electron. Look here, these are different species or different ions. They have same number of electron. Here actually 11 electron. Na plus mean 1 electron less. So there will be 10 electron. Actually here 8 electron. 2 minus mean 2 more electron. So 8 plus 2, 10 electron. Here 9 plus 1, F minus mean 1 electron more. F minus mean 1 electron more. So here 9 plus 1 10 electron. Mg, magnesium atomic number 12. So there will be 12 electron. Mg2 plus mean 2 electron less. So here also 12 minus 2 10 electron. Here 7 minus 7 plus 3 10 electron. 3 minus mean electrons more. Negative charge mean there is more electron. Okay, so you have to add here 7 plus 3, there will be 10 electron. So this type of species are called isoelectronic species. Isoelectronic species means a different species, they have same number of electron, they have different proton number different. Okay, also their ionic radius also different, they have different ionic radius, they have different proton number, but they have same number of electron. Clear? This type of species are called isoelectronic species. So look here, there are two cations, Mg2 plus and Na plus. Mg2 plus and Na plus, there are two cations. Okay, so here you can understand here, cation with higher positive charge, greater positive charge will be smaller size. Okay, so here Mg2 plus and Na plus, Mg2 plus it's greater positive charge, higher positive charge. Okay, so there are 12 proton, so it's there will be more effective nuclear charge in magnesium, and it will attract outer shell electron more effectively. Okay, so here the size of magnesium will be smaller than Na plus. Atomic radius of magnesium will be smaller than Na plus. Clear? Okay, next one we have to discuss here ionization energy. Periodic trend in ionization energy. Actually ionization energy mean amount of energy required to remove an electron from isolated gaseous atom. We have one isolated gaseous atom. From this isolated gaseous atom we want to remove one electron. Okay, amount of energy required to remove this electron, this energy called ionization energy. See here this is one isolated gaseous atom. Okay, gaseous atom. Okay, so from this gaseous atom we want to remove one electron. We will remove outermost shell electron, last shell electron. Okay, so after removing one electron, we know this gaseous atom will change to gaseous ion. After removing one electron, this element will change to positively charged ion, gaseous ion. Okay, so amount of energy required to remove this electron, this energy called ionization energy. Okay, ionization energy represented by delta H. Ionization energy represented like this, delta H, delta IH. Okay, delta H. Okay, and the unit of ionization energy kilojoule per mole. Unit of ionization energy kilojoule per mole. Okay, here this one represent first ionization energy. You can see here 1 and here 2. Okay, so this one represent first ionization energy, and this is second ionization energy. First ionization energy means this one, amount of energy required to remove an electron from gaseous atom. Okay, this energy, first ionization energy, after removing one electron, it is actually gaseous ion. Okay, after removing one electron, now it is a gaseous ion. Again same thing here. Again we have to remove one more electron from this gaseous ion. Again we have to remove one more electron from this gaseous ion. Okay, after removing one more electron, it changed to 2 plus. Before it was plus. Now one more electron removed, so it changed to X2 plus. Amount of energy required for this second process, it is second ionization energy. Amount of energy required for first process, first ionization energy, okay. And here amount of energy required for second process, that is second ionization energy. So second ionization energy, you can say amount of energy required to remove second mostly bonded electron, second mostly bonded electron, okay. So this is ionization energy, first ionization energy, second ionization energy. This is the equation for first ionization energy. I will give you ionization energy equation for sodium, chlorine, fluorine. How to write ionization energy equation, I will show you. Okay, so before that you understand what is ionization energy, how to represent ionization energy, unit of ionization energy kilojoule per mole, also how to write first ionization energy, second ionization energy. Also you remember here the value of ionization energy always positive, always positive, okay, because here always we have to give some energy, okay. This system always absorb energy to remove electron, okay. There will be one electrostatic force of attraction between positively charged nucleus and negatively charged electron. There will be an electrostatic force of attraction. To break this force, this system, this element always absorb energy, okay. So that's why ionization enthalpy always endothermic process, it is positive, clear. Also look here, we discuss ionization energy mean it is amount of energy required to remove an electron from an isolated gaseous atom, that is ionization energy. Ionization energy also we can say another way, it is a quantitative measure. It is quantitative measure of tendency of an element to lose electron. It is a measure, quantitative measure of tendency of an element to lose electron, okay. One element, how much tendency it's showing to lose electron, this measurement, tendency to lose electron, this measurement is ionization energy, clear. Okay, next one we have to discuss here successive ionization energy, successive ionization energy. See here, we know sodium atomic number 11, sodium atomic number 11, so there will be 11 electron, 281, 281, here 2 electron, here 8 electron, and this is outer shell 1 electron. We know amount of energy required to remove outer shell electron from one gaseous element, this energy called ionization energy. Amount of energy required to remove this electron, this is first ionization energy, first ionization energy, okay. So after removing this electron, it will change to Na plus. We know sodium, it is solid state, okay. For ionization energy, to check ionization energy, first solid sodium we have to convert into gaseous sodium, sodium in vapor state, okay. Then we will measure amount of energy required to remove outer shell electron from gaseous sodium atom. This amount of energy, it is first ionization energy. Here you can see here 1 delta H1, first ionization energy. After removing first outer shell electron, there will be 10 electron, so it will be Na plus, okay. Again we will remove second most loosely bonded electron. So second loosely bonded electron mean after removing this electron, next electron, this is next electron, okay. So we have to remove next electron, okay. So amount of energy required to remove second most loosely bonded electron from a gaseous ion. After removing one electron, now it is ion, a gaseous ion. This amount of energy called second ionization energy. Okay, so you can represent second ionization energy like this. Sodium, same like this, sodium gaseous ion. After removing one more electron, okay, here one electron removed, here also another electron removed. So here one more electron removed, now it is plus changed to 2 plus changed to 2 plus after removing electron, and it is delta H2, second ionization energy. You can remove one more electron, now it is Na2 plus gaseous state. After removing one more electron, it will be Na3 plus gaseous state, and this is delta H3, third ionization energy, and so on. This is called successive ionization energy. Okay, so we removed first electron, this is first ionization energy. Then we removed second most loosely electron, it is second ionization energy. Then we will remove third most loosely bonded electron, this is third ionization energy, so on. We can remove until complete electrons are removed. Okay, so here from this experimentally you can observe that second ionization energy will be greater than first ionization energy, third ionization energy greater than second ionization energy. Okay, what is the reason? After removing one electron, next electron it will be close to nucleus. Imagine here nucleus 2 8 1. Okay, you know structure of atom. Here nucleus, after nucleus 2, then 8, then 1. So after removing one electron, next electron it will be more close to nucleus. So attraction between nucleus and the outer shell electron will be higher attraction, and we have to give higher energy to break this bond. That's why second ionization energy greater than first ionization energy, third ionization energy greater than second ionization energy, so on. Okay, so this is successive ionization energy. Clear? Also here next point we have to check, compared to other element, first ionization energy of noble gases will be very high. Okay, in periodic table group 18 elements, helium, neon, argon, krypton, xenon, these are noble gases. These noble gases shows very high ionization energy because they have complete outer shell electron. They have stable electronic configuration. Their outer shell orbitals are completely filled. Okay, so they have stable electronic configuration. So they have very less tendency to lose electron. Completely filled orbitals. So very less tendency to lose electron. So we have to give lot of energy to break, lot of energy to remove this electron. That's why first ionization energy of noble gases or first ionization energy of group 18 elements are higher compared to other element. Clear? One more point you have to understand here, alkali metals compared to other element, group 1 element, that is alkali metals, lithium, sodium, potassium, rubidium, cesium, francium, these are group 1 elements. This element shows very less ionization energy because these elements are highly reactive. Okay, in S block element, S block mean group 1 and group 2, especially group 1 highly reactive. Okay, they have higher tendency to lose, just opposite to group 18. Group 18 very less tendency or no tendency to lose electron, but here group 1 they have higher tendency to lose electron. They are highly reactive elements. So here group 1 element or group 1 element or alkali metals, they shows very less ionization energy. Clear? Okay, next one we have to discuss here factors affecting ionization energy. Different factors affecting ionization energy. Okay, so here factors affecting ionization energy, there are two factors, atomic and ionic radius. Second one, shielding effect or screening effect. These are the two factors which depends on the ionization energy. First one, atomic or ionic radius. Here ionization energy decreases with increasing atomic radius or ionic radius. You can see here three different type of atom. Okay, here this is atomic radius, this is the third atom, and here atomic radius is higher atomic radius. So here distance between nucleus and outer shell electron, here nucleus and outer shell electron are far compared to other two because atomic radius higher. Okay, if atomic radius is higher, distance between nucleus and outer shell electron will be higher, and there will be less attraction compared to other less attraction between nucleus and outer shell electron, less attraction. That's why we need less amount of energy compared to others, less amount of energy required to remove outer shell electron. Okay, so generally we can say atomic and ionic radius, generally we can say ionization energy decreases with increasing atomic and ionic radius. Clear? Next one we have to look here, shielding effect or screening effect. Shielding effect or screening effect. You have here two examples. Okay, here this is first atom and this is second atom. Here first atom there is nucleus and outer shell electron. Between nucleus and outer shell electron there is no any single shell. There is no any shell or there is no any electron between outer shell and nucleus. Second case, this is outer shell electron and this is nucleus. Between nucleus and outer shell electron there are two shell. First shell 2 electron, second shell 8 electron. Here it is 2, 8, 1, and here just 1 electron. Okay, so in first case attraction between nucleus and outer shell electron will be higher. Attraction between nucleus and outer shell electron will be higher compared to this one. Okay, here attraction between nucleus and outer shell electron compared to this very less. Why? Between nucleus and outer shell electron there are many electrons, and these electrons make a barrier between outer shell electron and nucleus. These electrons are called inner shell electron. These inner shell electrons make a barrier between outer shell electron and nucleus. Okay, and this is called shielding effect or screening effect. Okay, shielding, they make a shield. Okay, they make a shield between outer shell electron and nucleus. Okay, that's why this nucleus cannot attract outer shell electron more effectively, because between nucleus and outer shell electron there is a shielding, so there is no effective attraction. Compared to this, attraction is less amount of energy required to remove outer shell electron, and ionization energy decreases. Okay, so these are the two factors which depends on ionization energy. First one, atomic and ionic radius. Second one, shielding effect or screening effect. Okay, also here one more point you have to remember. Here inner shell electron, there are many inner shell electron and this outer shell electron. We know electrons have negative charge, so there will be electron repulsion. These electrons and outer shell electron, there will be a repulsion. That's why this outer shell electron try to stay maximum apart. Okay, that's why atomic radius increases. Okay, inter-electronic repulsion. If there is many inner shell electron, there will be electron repulsion. Okay, because of electron repulsion, outer shell electron try to stay maximum apart from nucleus, and atomic radius increases. Also, it helps to decrease ionization energy. Clear? Okay, next one we have to discuss here trend in ionization energy. We discussed what is ionization energy, what are the factors which affect ionization energy. Next point we have to discuss here trend in ionization energy. Trend in ionization energy in periodic table. When you move from left to right across the period, what happened to ionization energy? When you move from top to down in the group, what happened to ionization energy? Okay, so look here, consider one period here: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Lithium, atomic number 3. Okay, so atomic number increases 3, 4, 5, 6, 7. Okay, atomic number increases accordingly. Atomic number increases mean number of proton increases. Number of proton increases mean positive charge of nucleus increases. So you can say when you are moving from left to right across the period, effective nuclear charge increases. Effective nuclear charge means positive charge of nucleus. That is, effective nuclear charge increases from left to right. Clear? But you can see here atomic number 3. So 2, 1. Here 2, 2. Number of electronic structure or electronic configuration I am saying here: 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8. This is subshell electronic, this is electronic configuration. So this electronic configuration saying that here 2 orbit, here 2 orbit, here 2 orbit. So number of orbit not increasing. It's mean their shielding no change. Shielding it is constant. Number of orbit it is constant. Okay, shielding not increasing, but what happened here? Effective nuclear charge increases. So nucleus attract outer shell electron more effectively towards nucleus. So size of atom decreases from left to right. Atomic radius decreases from left to right. Okay, so atomic radius decreasing mean outer shell electron become more close to nucleus, and outer shell electron and nucleus attraction is much higher, and we have to give more energy to remove this electron. So ionization energy increases. Generally there will be exception case. We will discuss its exception case later. Now you understand, generally ionization energy increases across the period. Okay, what is the reason? Reason: effective nuclear charge increases but shielding remain constant. This is the reason. Clear? So that is across the period. But when you check down the group, okay, when you moving from top to down the group, size of atom increasing. Group 1, lithium, sodium, potassium, rubidium, cesium, francium. When you are moving from top to down, atomic number increases, atomic size increases. Okay, atomic size increases mean radius of atom increases. Also inertial electron increases. Inertial electron increases. Also atomic radius increases. Because of this, ionization energy decreases. Down the group, ionization energy decreases. Reason: atomic size or atomic radius increases, shielding increases. Across the period, ionization energy decreases. Reason: atomic radius decreases. Shielding remain constant. Okay, this is the trend of ionization energy in periodic table. Okay, so here next one we have to discuss here some exception case. We discussed generally ionization energy increases across the period. When you check this period: lithium, beryllium, boron, carbon, nitrogen. So we are expecting ionization energy increases from lithium to neon. Ionization energy increases lithium to neon, but there are some exception case. So let us check here. When you consider beryllium and boron, look here beryllium and boron. So we are expecting boron shows higher ionization energy than beryllium, because boron more proton, atomic number 5 proton, higher nuclear charge. Okay, but the really it is wrong. Okay, so here experiment shows that beryllium shows higher ionization energy than boron. We are expecting boron shows higher, but actually beryllium shows higher ionization energy. Let us check what is the reason here. Beryllium atomic number 4, subshell electronic configuration 1s2 2s2. Okay, boron atomic number 5, 1s2 2s2 2p1, 5 electron, 1s2 2s2 2p1. Okay, so when you consider here two orbital, 1s2 2s2, 2 orbital, but here there are 3 orbitals, 1s2 2s2 2p1. So this is the outer shell electron 2p1. So here this is the outer shell orbital. So compared to this one, here comparatively more shielding experience here. Okay, here between 1s2 and outermost orbital, in between there is one more orbital 2s2. So this 2s2 orbital make a shielding. So here comparatively here shielding is higher compared to beryllium. More boron shows higher shielding. Okay, so outer shell electron and nucleus have less attraction compared to this, and less amount of energy needed to remove this electron. So here boron shows less ionization energy, because in boron more shielding. Okay, this is the reason here, more shielding. Okay, and see here second case, nitrogen and oxygen. Nitrogen and oxygen here. Oxygen atomic number 8, nitrogen atomic number 7. So we are expecting oxygen shows higher ionization energy. You can check the graph. In graph you can see the variations. Okay, there are many exception case. We are talking here 2 exception case. Okay, so here nitrogen and oxygen, we are expecting oxygen shows higher ionization energy, but actually nitrogen shows higher ionization energy. Clear? So nitrogen shows higher ionization energy. We can explain reason with help of subshell electronic configuration. We can explain reason with help of subshell electronic configuration. Nitrogen atomic number 7, 1s2 2s2 2p3, 1s2 2s2 2p3, 2p3 subshell electronic configuration in the form of box. We can say like this, we can do it like this. We know 2p orbital, p subshell contain 3 orbital, px, py, pz. So here 3 boxes. Okay, 2p3, each box contain 1 electron, half filled. So completely half filled it is. Okay, but oxygen atomic number 8, 1s2 2s2 2p4, here 2p4. The previous case it was 2p3, now it is 2p4. 2p4 mean one more electron, 1 2 3, and here one of the one box paired, 2p4. That's why here one box paired. Okay, this is the reason here oxygen shows less ionization energy. If the all boxes half filled, here it is half filled, but here it is one box is paired. One box paired, electron paired. If there is paired electron, there will be electron repulsion, inter-electronic repulsion. There will be inter-electronic repulsion. Because of this inter-electronic repulsion, outer shell electron try to stay maximum apart. Because of the repulsion, you know, if there is repulsion, it stay away to reduce repulsion. Clear? So here atomic radius increases, okay, because of inter-electronic repulsion, and less attraction between nucleus and outer shell electron, and less energy needed to break, or less energy needed to remove this outer shell electron. Okay, so here the previous case, here shielding, because of 2s2 there is shielding higher in boron, but nitrogen and oxygen it is 2p4 there is paired electron. Because of paired electron there is electron repulsion, or you can say inter-electronic repulsion. Because of this inter-electronic repulsion, outer shell electrons stay maximum apart, and this electron attraction between nucleus and outer shell electron will be higher. Attraction between nucleus and outer shell electron will be less, and less energy needed to remove this electron, and oxygen shows less ionization energy compared to nitrogen. So these are the things we have to understand about ionization energy. Clear? Okay, next point we have to discuss here: electron gain enthalpy, periodic trend in physical properties. Next point, electron gain enthalpy. One electron is added to an gaseous atom. Enthalpy associated with this process, it is called electron gain enthalpy. One electron is added to a gaseous atom. Okay, enthalpy associated with this process, it is called electron gain enthalpy. Look here, this is one gaseous atom. Into this gaseous atom we added one electron. After that it formed a gaseous anion. We know after adding one electron it will change to negatively charged ion. Enthalpy associated with this process, it is called electron gain enthalpy. Electron gain enthalpy represented delta EGH. Ionization energy we represented delta IH. Electron gain enthalpy delta EGH. This electron gain enthalpy may be positive, may be negative, depends on the situation. Electron gain enthalpy negative or positive. Electron gain enthalpy, this process may be exothermic or endothermic, depends on the situation. For example, here group 17 elements. We know group 17 elements, they have outer shell 7 electrons, and they have strong tendency to gain electron. That's why group 17 elements, they have higher negative electron gain enthalpy. Okay, one element showing higher tendency to gain electron. So such type of element showing negative electron gain enthalpy, negative value, means it release energy. Okay, so here group 17 elements, halogens, they have outer shell 7 electrons, and they have strong tendency to receive electron, and they shows higher negative electron gain enthalpy. Clear? Also some situation they shows positive electron gain enthalpy. Example, group 18 elements, noble gases. They have already stable electronic configuration. They have complete outer shell electron, so they have very less tendency to receive electron. Already their outer shell completed, so very less tendency to receive electron. So you want to add one more electron to noble gases, then you have to add lot of energy, then only you can add one more electron. You have to add energy, so system will absorb energy, so it will be higher positive value. Group 18 elements shows higher positive electron gain enthalpy, means the system absorb lot of energy to add one more electron. Okay, so electron gain enthalpy may be negative or positive. Negative group 17 elements, positive group 18 elements. Clear? After that, let us check what happened to electron gain enthalpy across the period and down the group. We know when we move across the period, size of atom decreases. So nucleus can attract outer shell electron more effectively. Okay, so electron gain enthalpy, negative electron gain enthalpy increases across the period. Negative electron gain enthalpy increases mean they shows more tendency to receive electron. Okay, because smaller size, so positively charged nucleus can attract outer electron more effectively. So across the period electron gain enthalpy increases. Clear? Next one, let us check down the group. We know down the group size of atom increases. Lithium, sodium, potassium, rubidium, cesium, francium. So atomic number increases, number of shells increases, size of atom increases. Size of atom increases. So positively charged nucleus cannot attract outer shell electron more effectively. So down the group negative electron gain enthalpy decreases. Negative electron gain enthalpy decreases mean less tendency to gain electron. Across the period negative electron gain enthalpy increases. Down the group negative electron gain enthalpy decreases. So we discussed down the group negative electron gain enthalpy decreases, but there is some exception case. Group 16 elements: oxygen, sulfur, selenium, tellurium, polonium. Okay, so when you moving down the group, according to this discussion, down the group negative electron gain enthalpy decreases, but here oxygen shows less electron gain enthalpy compared to other group members, compared to oxygen, sulfur, selenium, tellurium, polonium. Compared to other group members, oxygen shows less electron gain enthalpy. Also this case, group 17 elements, fluorine, chlorine, bromine, iodine. Also here fluorine, compared to other group members, here also exception case, fluorine not showing. Fluorine negative electron gain enthalpy of fluorine is less than chlorine. Okay, less than chlorine, because here also negative electron gain enthalpy of oxygen is less. Okay, negative electron gain enthalpy of oxygen is less than sulfur. Okay, reason for this, here oxygen and sulfur, their size compared to other group members, oxygen and fluorine, their size very small size. So into this small size, again we want to add one more electron, so there will be electron repulsion, inter-electronic repulsion. So it is very hard to add one more electron to oxygen and fluorine compared to other group members. Here oxygen and fluorine, their sizes small size, and when we add one more electron to this oxygen and fluorine, there will be one inter-electronic repulsion. Inter-electronic repulsion means electron repulsion. Because of this repulsion, oxygen and fluorine shows less ionization, less negative electron gain enthalpy. Here we discussed down the group negative electron gain enthalpy decreases down the group. Okay, there is one exception case, oxygen and fluorine compared to sulfur. Okay, according to this discussion, oxygen shows higher negative electron gain enthalpy than sulfur, but actually not like that. Also here, according to this discussion, fluorine shows higher negative electron gain enthalpy than chlorine, but actually not like that, because oxygen and fluorine, their size small. So when we add one more electron to this, okay, when we add one more electron to oxygen and fluorine, there will be inter-electronic repulsion. Okay, so it is hard to add one more electron to this type of elements. Clear? Okay, next one we have to discuss here electronegativity. Last point in this video, electronegativity. Electronegativity means tendency of an atom in a compound. Tendency of an atom in a chemical compound to attract electron pair towards itself. Especially this process happening in a covalent compound. For example, see here hydrogen chloride. Hydrogen and chlorine share one pair of electron. So here chlorine, non-metal, generally non-metal shows a strong tendency to attract electron pair. Non-metal shows a strong tendency to attract shared electron pair. Okay. This tendency of an atom called electronegativity. So electronegativity means tendency of an atom in a chemical compound to attract electron pair. This tendency called electronegativity. Okay, so here non-metals, they have strong tendency to attract electron pair. Metals, they have less tendency to attract electron pair. Okay, so generally we can say non-metals, their electronegativity very high, and metals, their electronegativity very less. Generally metal shows a tendency to lose electron. Okay, we know sodium, potassium, aluminum, their outer shell 1 or 2 or 3 electron. Okay, so this type of metals with their outermost shell 1 or 2 or 3 electron, they showing a strong tendency to lose electron. Generally non-metals, their outer shell 5, 6, 7 electrons, and they have strong tendency to receive electron. So generally we can say non-metals, they have higher electronegativity. Okay, and the metals, they have least electronegativity. Clear? So here electronegativity we can measure. Look here electronegativity, it is not a measurable quantity. Electronegativity, it is not measurable quantity. Also electronegativity, it is not fixed. Electronegativity value of an element not fixed. It vary with the situation. For example, you have HCl, okay, and another one here, H2O. Okay, so here hydrogen, the electronegativity of hydrogen will be differ in different situation. Okay, so electronegativity of any element, it is not fixed value, it is not measurable quantity. Okay, it vary with the different situation. Clear? So there are different scales, different projects and observations are did to measure electronegativity or to represent electronegativity. So here Pauling scale, it is very important scale. Pauling scale, it is very important scale. It represents electronegativity. Okay, in Pauling scale, electronegativity of fluorine is 4. Okay, this is the highest electronegativity value. In Pauling scale, it is 0 to 4. Okay, and here higher electronegativity value for fluorine. Clear? Also you remember, it is not measurable quantity and it is not fixed, depends on the situation, there will be slight changes. Okay, and here across the period electronegativity increases. Across the period, we know when you move from left to right, left side of the periodic table metals, right side of the periodic table it is non-metal. We discuss metals, they have less electronegativity, non-metals, they have higher electronegativity. So when you move across the period, electronegativity increases. Okay, similarly when you move from top to down the group, electronegativity decreases. Across the period, electronegativity increases, down the group electronegativity decreases. Clear? Also here you can understand electronegativity directly proportional to non-metallic character. Okay, here electronegativity directly proportional to non-metallic character. Elements with the non-metallic character, they have higher electronegativity. Okay, similarly you can say electronegativity, it is inversely proportional to metallic character. Okay, elements with a higher metallic character, they have least electronegativity. Clear? Also here I told you why non-metals have higher electronegativity, because their outer shell 5, 6 or 7, they have strong tendency to attract electron. Here electronegativity means tendency of an atom to attract electron pair in a chemical compound. Okay, that's why non-metals have higher electronegativity. So here we discuss what is electronegativity. Okay, and here consider one example. Here HCl, chlorine shows higher electronegativity because here chlorine, it is non-metal. So this arrow mark showing that electron pair move towards chlorine. Okay, and here Pauling scale used to represent electronegativity. Okay, in Pauling scale, fluorine has higher electronegativity. Fluorine, its electronegativity value 4. This electronegativity value is not fixed, it vary with a different compound. Okay, it vary with it vary in different situation. Electronegativity is not measurable quantity. It is not measurable quantity. Across the period, electronegativity increases. Down the group, electronegativity decreases. Electronegativity directly proportional to non-metallic character. Similarly, electronegativity inversely proportional to metallic character. Clear? So these are the things we have to discuss in this video. Okay, so next part, you can watch next part. Okay, so we will discuss periodic trend in chemical properties next video. Okay, so thank you for watching.